Let us commence this module by discussing about uncertainty. All decisions by the economic agents are undertaken in the scenario of uncertainty and risk. For making decisions, people form expectations for the variable by considering various types of information. One such hypothesis which is used by economic decision makers in the financial market is the efficient market hypothesis. It states that the current price of an asset reflects all available information about the value of the asset. Thus, no individual investor can gain extra profit at the same level of risk. Inventory, which the stock of raw materials and final output, is an important decision for all productive units. However, the optimal inventory decision seeks to minimize kinds of cost associated. Stochastic and deterministic are the two kinds of models of inventory demand, and each can be understood with different demand conditions like single period, periodic review at equal time intervals, or the process of continuous review. We will focus on the stochastic inventory demand models. After starting this module, you shall be able to know the various hypotheses of expectation formation, define efficient market hypothesis, identify the models of inventory demand, evaluate the difference between deterministic and stochastic models, analyze the stochastic models with varying inventory review systems. Now, we shall discuss about the uncertainty and expectations formation. Uncertainty is characterized by lack of perfect information and certainty. An economic entity makes decisions about many real-life variables in a partially observable or stochastic environment. Uncertainty is involved especially when we are considering the future value of some variable. This is because people do not have perfect foresight to know the future events. All such variables like inflation, prices of stocks and securities, etc. involve an uncertainty with regard to their future value. If we talk about financial markets and the prices of securities and financial assets, there is market risk associated with the prices of these assets. While investing in financial assets, investors are keen to know the performance of asset prices. For assessing the future prices of assets, investors form expectations. These expectations could be formed on the basis of several hypotheses, a few of which are: first, Markov expectation hypothesis. This is the simplest way to form expectations. It suggests that expectations are formed by looking at the most recent past value of the variable concerned. It assumes that the immediate past will continue into the next period. Suppose if we donate the price of an asset at time t by pt, then the expected price for the asset for period t plus 1 formed at time t in bracket p raised to the power e t plus 1 will also be pt. Thus, according to Markov expectations hypothesis, p raised to the power e t plus 1 is equal to pt. This means that we merely use the most recent value of the variable, that is p, in the present case to forecast future values. The apparent limitation of the Markov expectation hypothesis is that it does not take into account all the available and identifiable events that might change the future environment. Suppose if the variable is not only rising but rising at an increasing rate each time period, then the Markov expectations hypothesis will not only make systematic error but the forecast error will rise over time. Still, this hypothesis is a reasonable scheme of forming expectations at a time when the forecasting environment is quite stable. If, for instance, there is no inflation, then it might be rational to expect that the general price level in the previous period will stay the same next period. Second is adaptive expectation hypothesis. Under this hypothesis, people, while forming expectations in the present, adapt or revise their expectations for the subsequent periods by taking into account the forecasting errors that have already taken place. Considering an example to understand the method of forming expectation under this hypothesis. Let us say that we are forming expectations for the price of a security X. Suppose the current period is 2014 and the expected price of security in current period X raised to the power ET would have been expected in the previous period 2013. The actual price of the security is XT. The adaptive expectation hypothesis says that if this investor has to form expectations about the price of security for the next year, that is 2015, then he would adapt his expectation to the forecast error of the previous period. This means that the expectation will be influenced by the difference between the expectation for t plus 1 and that for t. Third is rational expectation hypothesis. This is the most sophisticated way of forming expectations. This hypothesis states that people, while forming expectations, take into account all the relevant information about all the variables which are expected to have any influence on the variable under question according to the relevant economic theory. Economic agents are assumed to be rational in the sense that they seek to best achieve their objectives, subject to external constraints on the choice of actions. Rational expectation hypothesis implies that the subjective probability distributions that the individual economic agents are assumed to use in making their decision in an economic model are consistent with the objective conditional probability distributed implied by the model. Let a variable y depends on its past values as well as those of the other values. Yt is equal to alpha 0 plus alpha 1 into y t minus 1 plus alpha 2 into x t minus 1 plus alpha 3 into z t minus 1. Expectation of yt will be given as e t minus 1 into yt is equal to alpha 0 plus alpha 1 into y t minus 1 plus alpha 2 into x t minus 1 plus alpha 3 into z t minus 1. Expected value e t minus 1 yt can be given by e t minus 1 into yt is equal to e yt upon I t minus 1. This is the rational expectation where expectation error is 0. This is not to say that this hypothesis assumes perfect foresight. Rather, it means that whatever error would be committed while forming expectations would be purely random. While determining the variable, there is some amount of human error which renders y as stochastic. It means that it has a random error term. Yt is equal to alpha 0 plus alpha 1 yt minus 1 plus alpha 2 xt minus 1 plus alpha 3 zt minus 1 plus vt, where vt is a random term which can be positive or negative. It is assumed to follow our probability distribution with mean 0 and constant variance. E t minus 1 into yt is equal to alpha 0 plus alpha 1 into y t minus 1 plus alpha 2 x t minus 1 plus alpha 3 into z t minus 1 plus e t minus 1 into vt. Mean value of vt is equal to 0. Under rational expectation, error equals the random error term. Moving on to discuss the inventory demand. All those economic possessions which are left idle for meeting some unforeseen needs of a production unit are referred to as inventory. Even though these are kept idle, but these have their own economic value. These are essential to maintain for all producing units, including different kinds of manufacturing units, retailers, factories and enterprises. Generally, it is the core constituent under the investment head of any organization. Huge proportion of production budget is set aside for material and other inventories. It is hard to deny that better management of inventory will result in the development of organizational productivity, decreasing cost and thereby contributing to efficient use of scarce capital. Inventory consists of raw materials, semi-finished stock, in-process supplies and finished or final goods. The basic objective for managing stocks of inventories is to decide the minimum essential requirement of stock that has to be kept while minimizing the cost associated with it. Thus, it aims to decide how much resources or inputs are to be arranged and when to order so as to lessen production cost while complying to the standard requirements. Inventory demand arises on account of various fronts, and because of the prevalent irregularity in the production inventory, no explicit inventory model has general relevance to the whole variant inventory situations. Consequently, a range of inventory models have been developed so far to handle specific inventory problems. Next, we shall discuss the models of inventory demand. Models of inventory demand are set up with the aim to minimize the total cost of inventory by either forecasting optimum inventory or by evaluating two or more inventory systems. The decision on how much inventory to demand is based on following three main factors. The cost of holding the stock, example, the interest rate foregone. The cost of placing an order, example, for raw material stocks or the operation cost of production. The cost of shortages, that is, the losses incurred if the stock is insufficient to meet all demand. The third factor is most difficult to ascertain and therefore this issue is generally addressed by forming a service level policy. This policy lays down in quantitative terms the minimum required percentage of demand that shall be met from inventory stock without any delay. The cost minimizing order quantity and reorder policies are in turn centered on the assumptions of the demand rate. There are two major methods which are generally used by industries to develop inventory backup estimates: deterministic and stochastic probabilistic method. The deterministic method is employed when the annual demand rate for a product or goods is constant and the single best estimation of inventory is built up on the basis of all the available and known economic information. The stochastic method, on the other hand, is employed when the demand rate is non-constant and non-deterministic and is described by a probability distribution. In this method, the known economic data is utilized to approximate the stock quantities and their corresponding probabilities. To understand the deterministic and probabilistic conditions even better, consider the difference between a certain and an uncertain situation. A deterministic condition is the one in which all the factors can be ascertained exactly. This can be considered as a situation of sureness since it is realized that whatever is measured, things are sure to work the same way. It presumes that the existing state of affairs are deterministic, hence optimization can be achieved in model setting. Here, whole of the information is known, therefore the factors can be ascertained with full confidence. But a deterministic situation is purely fictitious and thus rarely exists. In fact, certain level of uncertainty is always associated in a system. Stochastic models are thus employed in such scenarios of uncertainty. By writing down the probability distribution of the factors concerned, these models seek to lessen uncertainty. Probabilistic inventory models comprising of probabilistic demand and supply are nearer to the real situations and circumstances. The advantage with probabilistic approach lies in the fact that modeling a variable using a well-defined probability distribution brings us nearer to reality than the results that are achieved under deterministic scenario. But such models also create greater trouble in analysis and often become irrepressible. For the optimal item models, both deterministic as well as stochastic models of inventory demand can be employed depending upon the demand conditions. When demand is not known precisely, in place of building up inventory at constant rate, many factors such as the cost of shortfalls, the cost of arranging and the cost of stacking away are considered to formulate an optimal inventory plan. Stochastic models are realistic and thus most relevant for analysis. Thus, it can be concluded that optimal and most efficient inventory demand model is the one which seeks to minimize the cost of holding stock of raw materials or finished products. The choice of deterministic or stochastic models of inventory will in fact depend on the type of the industry. Now, we will discuss the stochastic inventory models. The deterministic model assumes that demand and lead time both are known and are constant. It also assumes independent demand. The customer demand is met through inventories which exist. These customers may be internal workers demanding material for production or external purchasers of final products. There is an accurate forecast of demand by the management. Under the stochastic model, demand and lead time are treated as unknown random variables and thus considered stochastic. Each of these random variables has a well-defined probability distribution which is considered while calculating the distribution of demand during the lead time. Whatever model of inventory demand is opted, it must address two questions. First, how much should be ordered when the inventory for the item is restocked? The answer to this question lies in the order quantity. Next is, when should the inventory for a given item be restocked? This requires the time of reordering, which in turn depends upon the underlying inventory system. Example, single period, periodic review at equal time intervals, or the process of continuous review. Both these decisions are taken with the objective of minimizing the total inventory cost, which is comprised of purchasing cost, setup cost, holding cost and shortage cost. The stochastic inventory demand model under each of the system is explained. First is a single period inventory model. Under the single period inventory model, the inventory situations in such that the order is placed just once in a period and the items which remain unsold cannot be transferred to the next period. This model is applicable for those industries whose inventory or final products are seasonal or perishable in nature. So, they cannot be carried forward in inventory and sold in future periods. A classic example of such goods include newspaper. Since newspaper is ordered daily for the latest news, the quantity that remains unsold cannot be sold the next day. However, it can have some salvage value when sold in the form of paper. Similarly, for seasonal and fashion clothing, the leftover stocks are not taken away forward, rather these are sold away by holding end of season or clearance sale. No items are carried in inventory to be sold in the next season or period. Since we are considering the single period inventory model, the inventory decision is made just once for the whole period and that too in the beginning. Therefore, we will do the incremental analysis for determining the optimal order quantity. Under incremental analysis method, a comparison is made between the cost or loss of ordering one additional unit C0 with the cost or loss of not ordering one additional unit CU. Thus, CO represents per unit cost of over-ordering and CU is per unit cost of under-ordering. In terms of probability, this can be stated as, let us say that P in bracket D is greater than Y is the probability that the demand for inventory is more than a certain level Y. P in bracket D is less than or greater than Y is the probability that the demand for inventory is less than or equal to the given level Y. Hence, the expected loss EL in the situation of overestimation and underestimation will be, for overestimation, EL Y plus 1 is equal to C0 P in bracket D is less than or equal to Y. For underestimation, ELY is equal to CU P in bracket D is greater than Y. The optimal level of order quantity Y star is determined where EL Y star plus 1 is equal to EL Y star. This implies that C0 P in bracket D less than or equal to Y star is equal to CU P in bracket D is greater than Y star. The probability theory states that P in bracket D less than or equal to Y star plus P in bracket D is greater than Y star is equal to 1, or P in bracket D greater than Y star is equal to 1 minus P in bracket D less than or equal to Y star. Substituting this in the last equation, we get C0 P in bracket D less than or equal to Y star is equal to Cu in bracket 1 minus B sub bracket D less than or equal to Y star. Solving further, we get P in bracket D less than or equal to Y star is equal to Cu upon Cu plus C0. This is the general condition for the optimal order quantity Y star in the single period inventory model. The determination of Y star in turn depends upon the underlying probability distribution. Second is continuous review multi-period model. After discussing the single period inventory demand model, we can extend our analysis to multi-period order quantity. Reorder point model. This model is different from the single period in the following context. A. Inventory decisions are made continuously with many repeating periods or cycles. B. Inventories can be carried forward to next period. C. In the inventory cycle, an order is placed at each reorder point. D. The time required to reach reorder point, time between subsequent orders and lead time are all unknown and cannot be determined beforehand. Under this setting, the two questions of how much to order and when to order are addressed as follows. First, the order quantity is approximated by applying the EOQ model, which assumes instant replenishment of stock with no shortages. This can be written as Y star is equal to under root 2kd upon under root h, where Y is equal to the order quantity, which is equal to maximum inventory level, k the setup cost every time an order is placed, h is equal to the holding cost per item per unit time, d is equal to the expected annual demand. Second, the other decision of the timing to order inventory, that is the reorder point, is taken by considering the expected demand mu per unit time, its standard deviation sigma, and z the standard normal variable which measures the standard deviation necessary to obtain the stock out probability. On this basis, the reorder point R can be stated as R is equal to mu plus z into sigma. The third is a periodic review model. In the above model, the continuous monitoring of inventory is a prerequisite whenever the reorder point is reached. It may happen sometimes that continuous review of inventories is required in multiple products periodically. Here, the continuous review becomes cumbersome. Thus, in these situations, periodic review model is favored. because this model makes it possible that the orders for numerous items be placed at the same stipulated periodic review time, assuming that for each product length of the review period is more than the lead time. The first equation of how much to order under this system is taken using the following relation. Y is equal to M minus H, where Y is equal to order quantity, M the replenishment or the maximum level, H the in-stock inventory at the time of review period. H will vary at each review period, which implies that order quantity will also vary in each review period, because every period the aim will be to order sufficient quantity so that the inventory position can be brought back to its the replenishment level M. This is determined subject to the consideration that the probability of stock out could be reasonably minimized and the order quantity at each review period is sufficient to cover demand for the review period and also the demand for the following lead time. If the demand follows the normal distribution, then for these two variables, that is the review period plus the lead time period, M can be generalized as M is equal to mu plus Z into sigma, where mu is equal to the mean demand during the review period plus the lead time period. Sigma is equal to the standard deviation of demand. Z is equal to the number of standard deviations necessary to obtain the acceptable stock out probability. Now, we will summarize what we have learned in this module. First, we have studied various about uncertainty and expectations. Second, efficient market hypothesis postulated that financial markets are efficient and investors do not reap any extra normal returns on their investments in financial assets. Third, the efficient market hypothesis exists with its three versions of weak, semi-strong and strong. Fourth, inventory demand models seek to reach the optimum inventory level, aiming to minimize the cost of shortages, holding, setup, etc. Fifth, stochastic inventory models can be classified as first, single period, second, multiple period, third, periodic review.